All right, good evening, everyone. We are recording now. I'll just start the screen share. And we're good to go. So today we're going to move on from, we had sort of our first real topic of inference last class with confidence intervals. And we learned about how confidence intervals was making some inference about the true population mean based on what we knew only from a sample. And hypothesis testing is a continuation of inference when we have a yes-no hypothesis that we want to answer. So it is related to confidence intervals, and we're going to discuss the relationship between the two. I will give you methods for testing hypotheses about a population mean and proportion. We will go through some common steps, sort of standardized steps of performing hypotheses testing, starting with writing out this thing called a null and alternative hypotheses, calculating your test statistics, your p-values, and applying these to some specific cases of one-sided and two-sided z-tests and t-tests for one sample. And we'll get a little bit into type 1 and type 2 error and power. All of this coming from chapter 4 from your textbook. So a brief review of confidence intervals. You remember that the population mean is something that there is a single answer for, and there's no uncertainty in that answer itself other than that we don't know what it is. So in the example of when you were all guessing my age, there is a right answer for my age, you just didn't know what it is, so there's uncertainty around it. Similarly, when we're talking about the population average of blood pressure level, of life expectancy, there is an actual number that would be right, but we have no way of knowing what it is. And so all we can do is to take a sample from that population and then draw inference about the true value for the entire population. And that is where inference around confidence intervals and hypothesis testing comes from. So in confidence intervals, we provide an interval with an associated level of confidence that we interpret as the probability that interval, which is the estimated mean plus or minus the margin of error, contains the true population mean. And another way to think of that is that if you take a large number of samples, there will be a certain amount of variation in the mean from sample to sample. And if we draw a confidence interval around each one of those means using the methods that you learned, if they're 95% confidence intervals, then 95% of those samples, your interval that you generate will contain the true mean. And so in other words, this estimated confidence interval with its given level of confidence provides a range of those population means that are consistent with what you observe in your sample. So the key to constructing this confidence interval is the center of it is pretty easy. It's just the mean of your sample. But the new thing that we covered is this margin of error, which is how far above and below that sample mean you need to go in order to contain your 95% confidence interval or any other confidence interval. And if the sampling distribution is normal, like for a large sample, and particularly for when the standard deviation is known and not estimated from the sample, and that 95% confidence interval is 1.96 standard deviations above and below the mean. Some little bits of scribbling to release my artistic urges. And when do you use the t-distribution instead of the normal distribution? So this 1.96 is only correct if your sampling distribution is normal. When is that not the case? Yeah.
Your sample size is small.
Yeah, if your sample size is small, and one other condition.
You don't know the standard deviation.
Sorry?
If you don't know the standard deviation.
And you don't know the standard deviation, you have to estimate the standard deviation as the standard deviation of your sample. That's right. And strictly speaking, if you don't know the standard deviation of your sample, you use the t-distribution, whether it's a large or a small sample. It's just that for very large samples, the t-distribution becomes very similar to the normal distribution. What's the difference? How is the t-distribution different than the normal distribution?
For small sample.
Yeah, and in particular, you use it when it is the distribution of the sampling means, or it is the distribution of your z-scores when that standard deviation is estimated from the sample mean, whether the sample size is large or small. It's the t-distribution. So for very large sample sizes, they're very similar. But what is the difference between those probability distributions? How does t-distribution differ from the normal distribution? Yeah.
It's wider.
It's wider, it has fatter tails.
Yeah.
Exactly. And when is that difference the greatest?
The smallest degree of freedom.
Yeah, the smallest degrees of freedom. And the difference is very small when you have large degrees of freedom. And that fatter tails, I don't think I actually mentioned this, but it becomes more extreme the further out from the center you get. So if you're looking at where, 0.0001 of the probability lies, that difference is much greater than at where 0.05 of the probability lies. So if you were doing a hypothesis test or a confidence, instead of constructing a 95% confidence interval, you're constructing a 99.99% confidence interval. The difference between the t-distribution and the normal distribution would be even bigger. And for a larger sample size, that difference would be even bigger. Even for a sample size of n equals 100 or something, there could be a pretty big difference still if you're looking way out there in the tails. So that's why I say that in reality, any time you calculate that z-score from an estimated standard deviation, the distribution of those z-scores is a t-distribution, regardless of sample size. It's just that they become similar, more and more similar as your degrees of freedom becomes larger. Yes, can I repeat that? So the key difference, or when you calculate this, let's see, like x, let's see if I can draw here, x bar minus mu0, which is the population mean under the null distribution, over s over square root of n. This item, if s is estimated from the sample, then this entire item follows a t-distribution. It doesn't matter what the sample size is, it's a t-distribution. So I don't want to confuse you too much by saying for large sample sizes it becomes very similar to a normal distribution. That's true, but the fact is it's still a t-distribution. And the further you get out from the center, the more of a difference there is. So no matter how large your sample size, if you went really far out from the center, you'd still see a difference. And when you're using the t-distribution, your confidence interval is the sample mean, as it always is, plus or minus the standard error, and instead of 1.96, it's the critical value of the t-statistic for alpha over 2. So for 95% confidence interval, that is a t for 0.025, and your number of degrees of freedom, which is n minus 1 for one sample. Any questions? So, let's see, just to give an example of these margins of error with for alpha equals 0.05, so that would be let me see if I can make this a little bigger so we can actually see. So alpha equals 0.05 and 22 degrees of freedom is 2.07. So that's what you use for a 95% confidence interval. And for alpha equals 0.5, it's not on here, but I calculated it, 22 degrees of freedom. That critical value is 0.69. So the reason I put this up there was because you remember I had you guessing a 50% confidence interval and a 95% confidence interval. And some of you had those being almost the same, and some of them they were radically different. Probably the ratio should be about 3 times bigger, going from, it's based on sampling. I mean, based on just guessing is another story, but if these are based on a sampling, the t-sampling distribution, then your 95% confidence interval is going to be about 3 times bigger than your 50% confidence interval. And you remember why the 95% confidence interval is bigger than the 50% confidence interval? Anyone?
1.96 standard.
Sorry?
Because of the 1.96 standard deviation to the both sides of the 95%. Larger than 50%.
So if it's a normally distributed sampling distribution, then the 95% margin of error is 1.96 times the standard deviation. But why, in general, are higher confidence intervals, why do they have a larger margin of error than lower confidence intervals? Yeah.
So if you include more values in the interval, you can be more confident that the values within.
Yep, that is a perfectly valid way to think about it. You can also think about it as if you have a certain variability in your sampling distribution as you draw samples. If you have a narrow interval, only a small fraction of your samples will fall near there. If you have a large interval, then a much greater fraction of your samples will fall in them. But the point is that yes, the greater the confidence you want to have, the more margin of error you have to have. Just like if you want to be completely confident in my age, you can't have any risk of being wrong, then you might want to guess from 1 year to 99 years old. Some of you almost did that. Okay. Yes.
In terms of, I understand it's safe to see the ratio, but is there any applicability of when you would use a confidence interval of 50%?
A 50% confidence interval?
That's what this is, right?
Yeah. I mean, yeah. I mean, 95% confidence intervals are very common, but I don't know, maybe there are cases where that's too, you don't need to be that confident. I don't know, if you were a bettor, I bet that there might be cases where you want to know what interval you need for even odds. But yeah, I mean, for publications in public health, I mean, it's only a degree.
I've only ever seen 95.
Yeah, confidence intervals. But mostly I point out the different things just so that you're not plugging in 1.96 all the time, so that you understand what that interval means and are able to calculate it for different values is the main value in it from my perspective, even if you only ever calculate a 95% confidence interval. So the key points to remember here are the relationship between sampling distributions and the confidence intervals. You remember that the central limit theorem gave us the relationship between a population distribution and a sampling distribution. And knowing that sampling distribution told us in what range we would expect a sample statistic to fall within 95% of the time. You should be able to interpret confidence intervals as the range in which you have a certain confidence that the population mean lies. Do you remember something it's not? Just in case I try to trick you on this later. Some interpretation that the confidence interval is not. Yeah?
That percentage of the population lies between.
Yeah, that was the one I had in mind. I'm sure there are other things it's not as well, but it's not a range in which 95% of individuals in the population lie, because it's not about individuals, it's about the population mean. And you should by now be able to estimate confidence intervals from a data set. Why hypothesis testing? And it's a good question when we have confidence intervals, and confidence intervals are very useful for giving us an estimate and the degree of confidence around that estimate. But it's not always possible to construct a confidence interval. There are some cases where you just cannot construct a confidence interval, and some cases where in any case, even if you do, you want a yes/no statement about some question, such as, does a population mean have a hypothesized value, or does some intervention cause a measurable effect relative to a control group? Some examples of these kinds of questions, yes/no questions, could be, do hypertensive smoking men have the same mean cholesterol level as the general population? This actually is a little bit vague in that, is this general population the general population of men or of men and women? Otherwise, you're comparing two different things here. Or does intermittent screening and treatment for malaria improve health and education of school children in a certain area? And I've posted a PDF in your Blackboard under today's weekly materials, just of an example of this last question. The article is titled Impact of Intermittent Screening and Treatment for Malaria Among School Children in Kenya, a cluster randomized trial. And I thought this article was interesting to put in here at this point because they're using a bunch of statistical methods that are way beyond this course. You're not going to do anything relating to hierarchical data until BIOS 3 and EPI 3. But you can already read a lot of the methods and results from this. It's a little bit maybe hard, let's see, to see here, but actually it's easier to see up there than down here. But you see point estimates of a proportion. You see risk ratios with confidence intervals and p-values. And you see results of a hypothesis test. No effect of IST was observed. So it's covering a lot of the kinds of ideas that we've already covered in this course, even if they're coming to those by different methods that we haven't covered. So the gaining confidence and in the interpretation of the things that we're learning right now will span to a lot of different kinds of inference and hypothesis testing, even if we don't get to those in this course. And just to note here in this conclusions, they're saying that this intervention is not effective in improving the health or education of school children, which is another way of saying that they failed to reject their null hypothesis. That's all I'm going to say about that now. I just wanted to use it as an introduction to hypothesis testing. The idea, the logic behind what we're doing is that our observations, our sample, comes from one of two population distributions. One is a usual, something that has been true in the past, or this is our control, our placebo, our this is what we will call our null hypothesis. For the second is a potentially new distribution that is induced by an intervention or by some different condition. And we don't know what this new distribution would be. In general, we have a hypothesis about what this usual distribution that has been true in the past is. To put this in a sort of a simple probability language, the analogy in terms of beans could be that I have a handful of beans and only a few of them are white. I have a bag of beans and most of them are white. Therefore, this handful that I have is probably not from this bag of beans because it's too different. That's really, it's as simple as that. You know what is in this bag, you observe this little bit, and based on how different it is from that bag, you either say, I don't believe it came from that bag, or it could be that it could have come from that bag. Another analogy, classic analogy, is the courtroom trial, where the defendant is considered not guilty until guilt is proven, and that would be the null hypothesis. So in the case of the bag of mostly white beans, you assume that any handful of beans that you have came from that bag unless you have evidence that it didn't. Or in the defendant, in the absence of any other evidence, you assume that your null hypothesis is what you assume to be true. And then in the courtroom, the prosecutor tries to prove the guilt of the defendant. And based on that evidence, they are trying to get the jury to choose an alternative hypothesis. And so that we will call HA or H1. That is the thing that is different from what has been originally assumed and the thing that requires evidence to prove. And it is only accepted when there is enough evidence to reject H0. So that's an important point, that the null hypothesis is the thing that you assume to be true in the absence of evidence against it. So in the example of the malaria intervention in Kenya, the null hypothesis would be that your intervention is not effective, and that is what you would assume to be true until you have evidence that it is effective. So your null hypothesis is no effect, and your alternative that you reject if there is evidence is that it is effective. And when you hear talk about evidence-based practice, that's where that comes from, that you assume that anything is ineffective until there is evidence that it is effective. This little table down here is a little quick reference that introduces to you these two types of error. So if your null hypothesis is true, or in this example, the defendant is truly not guilty, and there's an acquittal, you accept the null hypothesis, that's a right decision. Or if the defendant is guilty, the alternative is true, and the decision is a conviction or rejecting the null hypothesis, that's also a right decision. But there are two different types of errors you can make here. The first one is when the null hypothesis is true, but you reject it. And that is a type 1 error. So that's when really your intervention was not effective, but you still reject it. And this is the kind of error that the inference that you're going to learn is designed to control. That is the false positive, the false finding, the false evidence that we will be learning to control. The second type of error, though, which is just as real a kind of error, is where your alternative hypothesis is true. You know, your treatment really is effective, the defendant really is guilty, but you don't have enough evidence and you don't observe it. And that is a type 2 error. And that is something that you plan for in experimental design, but it's not a part of the hypothesis testing that we'll do. Does this make sense, these two types of error? You remember when I told you how there's a trade-off between sensitivity and specificity? How when we selected a threshold for a diagnostic test, you could increase one, but at the cost of the other? It's the same thing for hypothesis testing. There's a trade-off between your type 1 error rate and your type 2 error rate. You make one better, you make the other worse. So in the courtroom trial, if you want to make sure that you never release a guilty person, then you have to convict a lot of innocent people, and vice versa. So, these trade-offs are not just in statistics, but in life, and in kind of anything where you have an imperfect decision-making process, you're going to have to make some kind of a trade-off between these two types of errors and decide where the appropriate threshold is. In public health, that threshold is often just set at 0.05, but it is worth keeping in mind that that is an arbitrary threshold, and that does place a preference on avoiding type 1 errors. So it is a bit like the courtroom where in generally you do not want to convict an innocent person. That's what that 0.05 means. It's controlling this type 1 error rate to be at 5% of all of the cases where H0 is true. So a type 1 error rate of 5% in the courtroom means that you will convict 5% of the innocent defendants. So there is a relationship between confidence intervals and hypothesis testing in cases where you can construct confidence intervals. So when you are drawing a 95% confidence interval and you set z equals 0 where the sample mean lies and calculate the probability of, or the area where 95% of the probability of your sampling distribution lies, whether it's a normal distribution and it's between 1.96 and minus 1.96, or it is t distribution and it's something greater than that, then that is your confidence interval. So that's how you constructed confidence intervals. Whereas if you were thinking of this in terms of a hypothesis test, then that value of z equals 0 would be your theoretical mean under the null hypothesis. So under your null hypothesis, z, which was, remember, sample mean minus the theoretical, the mu0 population mean over s over square root of n. Under the null hypothesis, that is equal to 0. And any variation around it is just due to sampling variation. So you would then calculate z for your sample and reject H0 if it falls outside of this critical region where you expect 95% of your z's to come if you were to take a large number of samples. So the key difference here was that in the confidence interval, you set z, or you set the confidence interval at your z equals 0 plus or minus the margin of error. And so z equals 0 is x bar minus mu0. So your confidence interval is x bar plus or minus the margin of error, whereas in hypothesis testing, you calculate these critical regions and just give a yes or no whether or not your sample mean falls outside of them. So it's a slightly different calculation, but it involves these same critical regions. I'm going to give you a series of steps to take in hypothesis testing. And I really recommend that you follow them kind of literally as you start doing hypothesis testing. Even though in your software you can just take your data, run your t-test or whatever, get a p-value, and you're done. But it is really worth actually looking at these and being explicit about them so that you will know how to interpret those results, and especially this first step. So the first step, and you're implicitly doing these, even if you're just running the software, you're implicitly doing all of these steps. The first one being to state the hypothesis, both your null and alternative hypotheses. And this is reflected in the way you run your test. By the time you run your test, you've already defined a null and alternative hypothesis. And software generally will actually tell you what your null and alternative hypotheses were for the purposes of this test. The second step is to specify your significance level, alpha. That is your type 1 error rate. Type 1 error rate. The third step is to take your data, your sample of size n, and compute the test statistic. And for now, it's going to be, well, your test statistic is just your sample mean minus the hypothesized mean over your standard error. And it is the same. The test statistic is the same, but it will be compared to two different distributions depending on whether sigma is known or whether it's estimated as S. And from these distributions, you can determine your p-value, or if it is the t-distribution and you're using a table. So if you're using software, you'll always get an exact p-value. If you're doing it from a table, you will instead look up the critical value of your statistic and then compare. If you have your exact p-value, you compare that to your significance level alpha. If you're using a table, then you compare your test statistic to the critical value of the statistic. You'll get some practice doing this. And then based on this, either if your p-value is less than alpha, or if your test statistic is, or the absolute value of your test statistic is greater than your threshold, your critical cutoff, then you reject H0 and decide that there is enough evidence that your sample is enough different from that hypothesized null distribution to reject that null hypothesis and accept the alternative. And finally, state these conclusions in terms of your subject matter. Like you saw in the conclusions of that paper, where rather than just saying we rejected the null hypothesis, they say, or we accept the null hypothesis, they put it in terms of the subject matter and say this intervention was not effective at reducing the rates of malaria or increasing educational attainment. Go into these in a little bit more detail. Step 1, this formulation of the null and the alternative hypotheses. Again, this null hypothesis is the hypothesis of no difference from the past or ineffectiveness of your intervention, what you would expect if there is no change as a result of your experiment or the variable you're observing, or from the past. And if this null hypothesis is true, then any discrepancy that you see between your observed data and that hypothesized null population is only due to chance. It's due to sampling error. So that's like the key concept, I would say, of hypothesis testing. It is that you assume that the null hypothesis is true and then calculate the probability of your observation under that assumption. So you're stepping into it with a foregone assumption that your null hypothesis is true. It's a little bit counterintuitive. You know, you think you're going into it with an open mind. You know, maybe the null is true, maybe the alternative is true. But in fact, you're going into it under the assumption that that null hypothesis is true, because you have to make that assumption in order to know what that distribution is. So if under the assumption of the null hypothesis, it includes some statement of what that null distribution is. And based on that assumption, you can calculate the probability of what you observed. That's kind of the key kernel of hypothesis testing. And this is not just for the hypothesis testing that we're doing in this class, but all hypothesis testing. Every statistical hypothesis test you will ever learn is based on this idea that you assume that your null hypothesis is true, and then calculate under that assumption the probability of what you observed, or something more extreme than what you observed. As an aside, we will do a little bit of power and sample size estimation. When you do that, you assume that the alternative hypothesis is true. So it turns things on its head. But I don't want to get into that yet. For now, we assume that the null hypothesis is true. The alternative hypothesis is that there is a real difference between our observed data, or the distribution underlying our observed data, and the hypothesized null distribution. And if it is true, then this discrepancy is not just due to chance. There is a true difference in the populations that is also contributing to that difference. And so if the null hypothesis is very unlikely given the data, then it will lead us to accept this null hypothesis instead. So I will talk about two-sided and one-sided alternatives. A two-sided alternative means that your alternative allows for the possibility of the mean being greater than the null mean or less than the null mean. Written out as a formula that is like this. So H0 is that the mean of our population of interest is exactly the same as the mean under the null hypothesis. And the alternative is simply that the mean of our population of interest is different than the null mean. Doesn't matter how different it is, they might be just a little bit different, but just not exactly the same. This is another somewhat I think, challenging concept at first. Like, when are two things really ever identical, right? I mean, usually any two things, there's some difference between them. So why is the null hypothesis that they are really exactly equal? Well, the point is that is your null hypothesis. So if, and your alternative is that they're different, if you don't reject the null hypothesis, it does not mean that if you fail to reject the null hypothesis, it doesn't mean that that null hypothesis is true. It just means that you didn't have enough evidence to reject it. So in reality, if these two means are, very, very, there's a very, very small difference between them, then most likely we will fail to reject the null hypothesis, and we will accept the null hypothesis even if there is some small difference between the means. And this gets to power to detect the difference that we will talk about later. But in hypothesis testing, under the null hypothesis, you assume that the mean or any other sample statistic and there will be other ones that we'll look at, that it is the same as under this null distribution. And this also tends to have nicely interpretable meanings. Like, it means that an intervention is not effective. It means a drug is not effective. It means that these two populations, there's no difference between them in terms of some key attribute. So for example, is the blood pressure of smoking males the same as in the general population, which is 211 milligrams per 100 milliliters? If you were to write out these null and alternative hypotheses, your null would be that mu, what does mu mean here? Sorry? It's not the sample mean. Population mean. That's a very important distinction. It's the population mean. Because hypothesis testing is about population means. There's uncertainty because we only have a sample, but we're making inference about the population mean. So it's the population mean of what? This mu. In this example that I'm giving right here, what is mu? Sorry?
Blood pressure of smoking males in a general population, that would be the population of itself, of the mean.
Yeah, it would be the mean blood pressure among all smoking males. So if you were to take all smoking males in your, I don't know if this is in the United States, say it's in the United States, and if you knew the blood pressure of all of them and averaged them, that's what mu is here. And our null hypothesis is that that value is 211 milligrams per 100 milliliters. Any questions? We haven't done anything yet with two samples, and we won't actually do the nuts and bolts methods for two samples until the next class. But I do want to write down the null and alternative hypotheses. So instead of there being that mu0, the hypothesized population mean, we're looking at two populations here. So, so the null hypothesis is that the mean of those two populations is the same. So this looks very similar to here, where it was mu0. The difference is that here, we don't have exact values for either one of these means. All we have is samples of both of them. So in this case, I had 211 milligrams per 100 ml as a known population average from somehow. I don't know where this would have come from some very large sample size from a nationwide study. But the point is that this information is not coming from a sample. Whereas in two sample tests, we are doing a hypothesis test about the means of two populations where we don't have the population mean of either of them. All we have is those two sample means. And the alternative is that those two population means are not the same, or that the difference between them is not zero, equivalent. So for example, the paper that I showed the abstract of, does intermittent screening and treatment for malaria affect the prevalence of anemia in school children? So the null hypothesis here is that the prevalence in the control group is equal to the prevalence of anemia in the treatment group. The alternative is that those two prevalences are not equal. So in this case, we don't know what the prevalence is in either group. All we have is a sample from each of these groups, from a control and a treatment group. You notice how I have a very specific kind of format that I write each of these out in. I want you to do this too. When you do your assignments, when you do your exams, there are going to be questions that ask you to write out your null and your alternative hypotheses. And I would like you to do them in a formal way like this, because these really have meaning in terms of how you interpret your results. And the fact that, you know, that this is a mu, you remember, like right in the syllabus, I say I use Greek letters for population parameters and equivalent Roman letters for samples. We don't have that for the prevalence, but we usually use a p hat for an estimated prevalence from a sample. Writing these out shows that you know that these are hypotheses about the population. That it's not just that, you know, your null hypothesis is that the sample means are the same, because that's not what it's about. It's about the population means being the same. And it also shows that you know what your alternative to that null hypothesis is. So there are different alternative hypotheses that you could have. Because there's this thing called one-sided alternatives, where, so the null hypothesis always includes an equality of no difference from the null, but it can also include an inequality. So in this case, our null hypothesis is that the mean of our population of interest is less than or equal to this null mean. And the alternative is just that it is greater. And you can have a one-sided alternative for the two sample case as well. And that equality could be in either direction. Having introduced this to you, I want to tell you to use it very sparingly and probably never use it unless there is a reason to use it before you, like in your study design planning phase. The fact that you know, you're sure that your intervention would never, you know, increase the rate of malaria is not a reason to use a one-sided alternative, or that you're sure that your treatment can't actually be harmful. That's not a reason to use a one-sided alternative. Because if your null hypothesis is true, your two-sided null hypothesis, then you actually will observe values above and below for the test statistic in your sample. And if you're using a one-sided alternative, then you're twice as likely to reject the null hypothesis as long as your statistic is on that right side. So it makes it easier in general to reject your null hypothesis. And that is one of the reasons why it's almost never used. and many journals won't even accept the one-sided alternative test. So yeah, that one-sided test is controversial because it gives smaller p-values, in particular if you decide on the directionality based on your data. So the classic mistake to make there is to say, you know, I see that the rate of anemia is lower in my sample, in my treatment group than the control group. So I'm going to use a one-sided test where the alternative is that the mean in the treatment group is lower, and that doubles your p-value, or sorry, it halves your p-value and makes it more easy to find a statistically significant result. When in fact, if your null hypothesis is true that it's ineffective, then you have increases and decreases in the rate of anemia just as often. So any one-sided test must be clearly justified in advance of the test, and there should be no reasonable possibility of another alternative hypothesis. So a two-sided alternative hypothesis should just be ruled out a priori. The only sort of justifiable case that I can think of is these equivalence trials where you're doing a comparison between, say, a brand name drug and an alternative generic, where there is no way that it's the same drug, and all you're trying to do is show that it's not inferior. So if it's the same, that's okay. If it's more effective, that's okay. But you only want to reject your null hypothesis if it's less effective than the standard brand name drug. That can be a justification for a one-sided test, because it's also then more sensitive to picking up an inferior generic alternative. A lot of step one. Step two. Choose that significance level alpha, which is your acceptable type 1 error probability, which is the probability of rejecting your null and accepting the alternative, even though the null is true. And typically, it's taken to be 0.05, almost always. There have been some movements I've read lately, people arguing to move towards 0.01, just with concerns about things like so-called p-hacking, where there's a habit of investigators to try a few different things to try to get under p equals 0.05, and that becomes much harder to do with a p-value of 0.01, but still. This alpha plays the same role as that error probability and confidence intervals, so the probability of the true mean lying outside of your confidence interval. And this type 1 error rate is your probability of rejecting H0 when H0 is true. So if you just take one thing from it, just take this bold-faced bit. Alpha is the type 1 error rate, and it's the probability of rejecting H0 when H0 is true. Number 3 is calculating this test statistic, which depends on what your null hypothesis is and what your type of data are. In general, though, any test statistic measures the difference between the observed data and what is expected when the null hypothesis is true. So generally, it's something that is small for the null hypothesis and becomes larger, either more positive or more negative, the less likely or the more different your sample is from that null distribution. For means or proportions, this is going to be the z statistic or the t statistic calculated in the same way if you don't know the standard deviation. And the reason that you calculate this test statistic is because for these instances where we have tests, we know the sampling distribution of that test statistic under the null hypothesis. So if your null hypothesis is true, you will know that your test statistic follows that standard normal distribution or follows the t distribution. You know what the distribution is under the null hypothesis. And based on that, you can calculate the probability under the tails of this distribution of observing your test statistic or something even further out on the tails of that sampling distribution. Step 4 is to calculate that p-value from your known hypothesized null distribution, and it is the probability under the tails of that distribution from your test statistic and everything beyond it. And generally, it's a two-tailed distribution. It's the probability to the right, if it's a positive test value of the test statistic, plus the value on the left from the negative of your test statistic, which for these symmetric distributions is just twice the probability as under that one tail. Or put another way, what's the probability in the tails of your sampling distribution beyond that value of the test statistic that you observed in this one sample? And as I mentioned, all hypothesis tests go through essentially this process of calculating a test statistic for the sample and then comparing that to a hypothesized distribution under your null hypothesis and calculating the probability of what you observed under the null hypothesis. And then based on that probability, if it's a fairly large probability of what you observed, then you consider it to be consistent with the null hypothesis and you accept the null hypothesis. If there's a low probability of it having occurred under that null distribution, and you reject your null hypothesis and accept the alternative. And then finally make conclusions about your question at hand in terms of the subject matter based on the results of the hypothesis test. So 5-step process. I won't go through them again. I'll spare you. So going back to this example, I just thought it would be interesting to discuss it a little bit. Take a look here. I don't know. Is this readable? We might have to have you take a look at this over the next week, and then we can take a look at this next week. I had a few questions about it. What the outcome variables are, what are the null and alternative hypotheses, the significance level, the p-value, and whether H0 was rejected. So I'm just going to ask that you take a look at this. The paper is there in Blackboard over the next week, and then we'll come back to this again at the start of the next class and discuss these questions. Going back to our survey. I'm doing it finally here. I'm giving up my age. I'm almost 44. So I'm putting that as the null hypothesis. That's the true answer. And setting up hypothesis testing around, do I look my age? So under the null hypothesis, which is that there's no change from the usual, which is my actual age, then your average point estimates would be, the average of your point estimates would be equal to 43.9 years, and there would be random variation above and below that, but the average would be 43.9. And the alternative is that it's not 43.9, above or below. So we'll let alpha equal 0.05 and then calculate the test statistic. So the mean of your guesses, there were 17 of them, was 39.9. And the standard deviation was 5.4. So what's the test statistic here? I didn't actually put it on the slide, so we could write it out. All right, can you give me some help here?
39.
Sorry?
39.9.
39, okay. 9.9 minus 43.9, yeah. Maybe I should be doing this in Excel so that I can actually get an answer. Putting some pressure on us to get it right here. Let's see. Come on, you can do it. Okay. So let's see, X bar was 39.9. Make this bigger. Mu was 43.9. S was, what did I say? 5.4. And N was 17. So let's see.
7. Yeah, you put 5.7.
Oh, sorry, what was, should it be?
5.4.
5.4, thank you. Okay, so T. So T is equal to, it's X bar minus mu over S over square root of N. Which is equal to, so it is N6 minus I6 over J6 over square root of K6.
To leave H,
Oops.
H6, not N6.
And, oh yeah, there we go. Thank you. That's why we have, that's a really extreme T. Okay, that looks a little bit more reasonable. It's about -3. What's your guess? Is it going to be significant or not? Reject?
Oh wait, -3. I thought it was a point.
I'll add minus 3.05. Who thinks it's going to be reject the null? put your thumbs up if you think we're going to reject. Who thinks we're going to accept the null? Who's not sure? And more people are just keeping a secret. Okay, well, let's see. So, I did this here just by, so first I looked up wait a minute, n equals 17. This should have been 17. Let's look it up on here. The critical value for 17 degrees of freedom. Degrees of freedom, 2.11 would be the critical.
Should it be 16?
Sorry?
16.
16 degrees of freedom, thank you, 2.12. Did I get that right up here? No, I got it wrong there too. So this, I'm just gonna write. This should be 16. And this should be 2.12. So since our actual value is -3, now who thinks we're going to reject the null? Who thinks we're going to accept the null hypothesis? Who thinks we're going to reject it? Okay, like 5 to 0. Well, you're right. We're going to reject the null hypothesis. Just to take a look at it with software here, I did this in R just by taking this vector of ages and comparing to mu equals 43 plus 11/12 months. Gives me this t statistic of -3. 16 degrees of freedom, p-value is 0.007895. So p-value is less than alpha of 0.05, so I do not look my age.
So we got the p-value from either the chart or
from the chart we only compared our t statistic to the critical value of 2.12, and since the absolute value of ours was greater than 2.12, we reject the null hypothesis. No p-value from the chart, not from a chart of t statistics.
Oh, yeah.
Yeah, there's just not enough detail on here, but from software, you get the actual p-value. So I was happy to see that I don't look my age, and I would in fact conclude that I look something less than my age. Oops, sorry, I didn't update this from last year. So last year I did look my age. Reject. Reject. All right. I'm going to skip over this next test. It's the same thing, except that I provided the population standard deviation. So you're using the table of the standard normal distribution instead of the table of the t distribution, calculating a z statistic and calculating a p-value or the statistic, and making your decision on null hypothesis. So I'm going to end with a note on testing proportions that for large sample sizes on proportions, let's say greater than a sample size of 30 and at least 5 in each group, you can proceed the same way as for continuous data, except considering your variable to be zeros and ones. And so your mean then is interpreted as a proportion, but your sampling distribution is still a normal distribution, with the only difference being that you have a different formula for calculating the standard error. The only difference, but you can otherwise then proceed the same as you did with the z-tests for confidence intervals and for hypothesis testing. Lots of examples in here for you to enjoy later, but I'm not, oops, I'm going backwards, that's why. I also wanted to make this note that, that you can also use your confidence intervals for a single sample to perform a hypothesis test, in that you construct your confidence interval, and if it contains your mu0, your hypothesized population mean under the null hypothesis, then you don't reject H0. If the population mean falls outside your confidence interval, then you do reject H0, and you will do it with exactly the same frequency as if you do it with the hypothesis testing approach. They're equivalent. So the key point there is that for one sample, you can use your confidence intervals to decide whether to accept or reject the null hypothesis based on whether your constructed confidence interval contains your population mean under the null hypothesis. However, for two samples tests, you cannot do it by looking at the overlap of two confidence intervals. That's not a valid hypothesis test. So, and that is a common misconception that I want to make sure that you do not make. So if you have two samples, you cannot just construct two confidence intervals and see whether they overlap. In fact, what you can do is construct one confidence interval for the difference in the means of those two samples. And that you can use for a hypothesis test. But we will get to that next week. Boy, I'm going long today. I introduced to you type 1 and type 2 error before. So you just have a bigger table of it here. I'm gonna quickly go over this, but I just want to introduce a little bit more to you these basic ideas about power before next class. As I mentioned, there's a trade-off between type 1 and type 2 error. That type 2 error, which is when you fail to reject the null when the null is false, it becomes less frequent the bigger the difference are. So another way of seeing that is that it's easier to see a bigger difference. So if your true difference is big, you're going to tend not to make type 2 errors. This thing called the power is actually just 1 minus the type 2 error rate, so it increases. It's your power to detect that difference is greater when the difference is greater. Type 2 error decreases as your standard deviation decreases, or as n increases. So both of these things reduce the width of your sampling distribution. And so they, again, make it easier to see differences between two samples or between one sample and a hypothesized mean. Things that make your sampling distribution narrower, which mean a narrower standard deviation or larger sample size. All these things are related. Type 1 error is just fixed, right? That was step 2 of your 5-step program, you just decide on the type 1 error. And generally in experimental design, you want power to be as high as possible through the design of the study. Alpha is the thing that protects us from spurious results, from rejecting the null and reporting findings that are false. And power is the thing that protects you from negative results when some important difference really is present, but you haven't collected enough evidence to observe it. And we will return to power. So the t-test, I think I've told you enough about. Same thing as the z-test, just a different null distribution. And we're really at the end now with some conclusions. First of all, and this is a very important misconception, if we fail to reject H0, is the probability that H0 is true equal to 1 minus alpha? And I put hint no, 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 just to make sure that I didn't get you thinking the wrong way, even for a second here. No. If you fail to reject 0, it doesn't tell, to reject H0, that doesn't tell you anything about the probability of H0 being true. That just tells you about the probability of observing your sample if H0 is true. You can fail to reject H0 simply because you haven't collected any evidence. So, or because your alternative, your true alternative is very similar to H0, is not evidence that H0 is true. It's just that you have failed to collect evidence to prove the defendant's guilt or to prove the effectiveness of your program. And that does bring me to one conclusion, also that statistical significance is not necessarily the same as practical significance, in that with very large sample size, it's possible to reject the null hypothesis for very, very small differences between population means that might not be practically important. And similarly, practically important differences might not be detectable in a hypothesis test if you have insufficient sample size. With that, let's take, are there any questions before we take a 5-minute break and go over to the lab? All right, thank you.